talk a little bit more about the science of intelligent design, and exciting to hear what was spoken about before me. I'm going to connect to some of the themes that we heard about in the prior talks. I'm going to be talking more about the science than I did yesterday evening, if you were here for yesterday evening's talk. And I'm going to be talking about molecules that are known as proteins, understanding that at this time of the day before lunch, when I mention protein, most people are thinking of this, and I am as well. But I'm actually going to be talking about proteins at the molecular level, these intricately shaped molecules that do the molecular tasks that are essential for life to function. Okay, they do chemistry, they make machines, as you heard about from Mike Behe. They do all kinds of things, move things around, make scaffolds. They are the workhorses of life at the molecular level. Now, would it be better if we had these lights off, by the way? Can you see well? It might be better if we had these lights off, if that's possible. No? Yeah, is that better? Okay. I've shown here just a sample of the thousands of different shapes that proteins take. And the reason, I think these are beautiful molecules, but the shapes are more than beautiful. They are essential to how these things function. And I want to give you an example of how shape affects function at the molecular level. This is not a protein, this is an RNA molecule. And in this form, it is useless to the cell. It needs to be, in order for it to be useful to the cell, it needs to be examined down here. And based upon what is seen down here, it needs to be modified up here. Okay? And there's a protein that does the examining and the modifying. And the protein looks like this. Perfectly shaped to hold the RNA molecule, to examine what it looks like down here, and to modify it up here based upon what it sees down at the bottom. And usually, biologists prefer to look at proteins in a different representation that's much simpler than looking at all the little sticks of the atoms joined. And we usually have these coils and ribbons to represent the overall folded structure. But this shows you, in a very clear way, how the shape, just like the shape of a tool is important to what the tool does, the shape of a protein is crucial for how the thing works. And so the first question we have is, how do these marvelous things, proteins, originate? And there's two elements to that question. One is, how do they originate within the cell? So how does a cell make proteins? And the answer to that is well known, or at least parts of it are well known. The answer is that genes that are carried on DNA carry the sequence instructions for cells to arrange amino acids in a chain. There are 20 different amino acids. They get arranged like beads on a string according to the sequence instructions carried on a gene. And once that is done, you have just a long floppy chain of amino acids like beads on a necklace, unless that sequence has the properties that enable it to do this, to cluster amino acids together to form a locked three-dimensional structure like the one that I just showed you that does that work on that RNA molecule. Well, this is a cartoon. They don't really look like that. They don't even really look like this, but this is the representation that biologists use to show the kind of structure you have in a folded protein. Two components you see are these coils that are called alpha helices, and the arrows that are called beta strands, and those make up together, they make up all of these structures of these folded proteins. It isn't really beads on a string. They're really amino acids, and the 20 amino acids differ in these appendages that stick out from the chain. And these are crucial. The chemical properties of these parts that stick out, of the amino acids, are the crucial elements that allow the physics to work for these things to collapse and form their folded structure. If you don't have the right interactions between these appendages, the floppy chain will stay a floppy chain, and it won't stay a floppy chain for long because life doesn't like to have floppy proteins, and there are enzymes that will chew them up and chop them up and recycle the amino acids. So that's the first question, is where do proteins come from in the cell? But that begs another question, which is how did cells first get these things? How did they get the genes to make these proteins in the first place? And this is the question that I've been addressing for over 25 years now, going in the lab, trying to find out how hard it would be for a Darwinian process to come up with these things. And if a Darwinian process can't do it, then what process does do it? Okay, now, most people trained in biology, if I ask that question, where did these things first come from, the answer will be natural selection, because that's the answer to all origins questions in biology, or at least that's the answer that we're given when we study biology. And of course, this originated with a book that was published in 1859, written by Charles Darwin, but it continues to this day. And there are many biologists, though not all, who think that natural selection is the answer to all of life's design. Interestingly, I was at a meeting last November in London that was convened by the Royal Society of London, where there were a number of biologists who don't believe that natural selection is what organized life, and they were arguing back and forth. There were a few classical Darwinists, but many of the younger biologists don't actually believe in Darwinism anymore, and yet they're not favoring intelligent design. So it was an interesting meeting where there was conflict between two camps, neither of whom were wanting to acknowledge intelligent design, although there were a good dozen intelligent design advocates at the meeting. We weren't allowed to speak, but we were there. Okay, so a quote about natural selection from Richard Dawkins. Natural selection is the blind watchmaker. The living results of natural selection overwhelmingly impress us with the appearance of design as if by a master watchmaker. Graham Bell, who was actually at that London meeting, and I met him for the first time, wrote this in one of his books: living complexity cannot be explained except through selection and does not require any other category of explanation whatsoever. In other words, all of this and more is explained by natural selection. Well, when I first approached this problem, I realized that tackling things like this is too hard for me. I wanted to look at the very simplest components of life and ask whether natural selection can explain those, and that's what took me to proteins and individual genes. Here's a problem, though, with natural selection, and it's this problem that made me in particular interested in studying individual protein molecules. Because these floppy beads on a string do absolutely nothing. They're no good to a cell whatsoever. In fact, they're even harmful to a cell if they don't fold into something like this. You have seemingly a problem for natural selection, because natural selection rewards organisms for having genes that are good, and yet the gene that encodes something that doesn't fold is not good until it folds, right? So the question is, how hard is it to get a gene sequence that just happens to produce something like this that folds? Because if it doesn't, then it can't be selected. It has to be like this in order to be selected. And you can think of this as sort of a blind search. If you want to ask whether Darwin's theory works, there was nobody who crafted these things, these beads on the string. They had to just throw beads on strings and see what works. And it's kind of like typing randomly and seeing whether something profound comes out of it. You know the proverbial monkey typing Shakespeare on a typewriter is not apt to produce anything particularly useful. Probably will be something more like this. I don't need to translate this. That's not English or Portuguese. Not something like this. This is from the last chapter of the book of Job. I have uttered what I did not understand, things too wonderful for me which I did not know. So we could imagine doing experiments that ask how hard it would be for a random sequence, not a sequence of letters in this case, but a sequence of amino acids to produce something like this. And I spent a number of years in Cambridge trying to find a way to do this in the laboratory. I didn't use monkeys. I used random mutagenesis techniques to put random amino acids in this protein. This is an enzyme called beta-lactamase. It is an enzyme that is loved by bacteria but hated by humans. This is the enzyme that enables bacteria to survive in the presence of penicillin antibiotics. So it's because of this that we had to move on from penicillin to other antibiotics. Well, after years of work, I published results in this paper that came out in the Journal of Molecular Biology in 2004, and I had measured experimentally how rare these functional sequences of amino acids are, how hard it would be to stumble upon a string of amino acids that folds to form a functional enzyme. I'm going to give you the number in a moment, but I want to first do a little illustration to help you appreciate the difficulty of searching a large space and finding a small target. And I wonder if I could get a volunteer to help me with this demonstration. Anyone? Yes. Come on up. Yeah. What I'm going to do is put a laser point on the ceiling, somewhere on the ceiling. You're not going to watch. You're going to have your eyes closed. I'll use this laser. You'll use this laser. And then what I want you to do, I'll tell you when to do it. Have your eyes closed and point up, not in people's faces. And you can wander your laser point around anywhere on the ceiling. Do it slowly enough that people can see your point, and we'll see if by chance your point happens to overlap my point. Okay? So close your eyes. Hold on, don't go yet. Okay, go. You're doing fine. Okay, you can open your eyes. My point was over there. Yeah, so you're way off. Now, but of course, it's impossible, right? Now, I use this as an illustration because it helps people to see what the basic problem is if you have a very large space, in this case the ceiling, the area of the ceiling, and you have very small dots on that space. And one of them is fixed, representing a target, right? So like the set of typed sequences that we would say, hey, that's an interesting sentence. And the others, the ceiling is all possible things that a monkey could type, or all possible ways you could string amino acids on a string. And my dot was the target of strings of amino acids that fold to form a functional protein, a very small fraction of the total. And what makes the task so difficult is the ratio between the size of the laser dot and the size of the ceiling. But as difficult as that was, I'm sure if he had done this, if we had stayed here for hours and hours, eventually his dot would have hit my dot, right? But suppose we made it a little bit harder, okay? Suppose we used pinpoint laser beams, and suppose we were in a bigger building with a larger ceiling than this. I happen to live close to, in Seattle, the largest building in the world in terms of volume. It's the Boeing factory in Everett where they make the Boeing aircraft. So imagine if we had pinpoint laser beams and we were in this building with all the walls and all the equipment taken out, and someone blindfolded were wandering their little laser dot around trying to find a fixed dot on that ceiling. Well, you could spend a good chunk of your life doing that and it would never overlap. The problem of finding a functional protein is considerably harder than that. So now imagine this problem. Instead of a pinpoint laser beam, we have laser beams that are the size of a hydrogen atom, which is very small. And instead of the Boeing factory ceiling, we have this for our ceiling, the visible universe. So at the furthest reaches of the visible universe, 14 billion light years away, we have this huge canvas, we imagine, and we imagine these hydrogen atom laser beams projecting on that canvas. That is the difficulty of the problem of searching through that space to find a sequence of amino acids that folds to form a functional protein. When you put the picture like that, you realize this is not possible. There's no accidental process. No random search is going to do that. Nothing is going to succeed other than intelligence. So conclusion, new proteins can't be found by natural selection because they're too rare. And that raises a question that we addressed also in the laboratory, which is what can natural selection do? This is very much related to what Mike was talking about with the edge of evolution, except in our case, we went to the lab to try to show, can we find something that natural selection can do and can't do, and try to discern what is possible and what is not possible. I think our reason for this was we didn't want to only publish work that says evolution doesn't work. We want to acknowledge what does work and show that it works so that we're being very fair about reality, about what works and what doesn't work. Okay, so I'm going to talk briefly about 3 different experiments that I and my colleagues have done next. And I'll title this part of the talk, The Truth About Natural Selection, Good, Bad, and Ugly. So good, bad, and ugly will refer to these 3 different experiments, or the results of the experiments. First, the good, okay? This is a reference to a Clint Eastwood film. Probably very few people have seen it. Okay, yeah, all right. Here's the paper that was published that describes the work that I'm going to talk about next, where natural selection actually does something reasonably well. This is work that was done by myself and Ann Gager at Biologic Institute. And what natural selection does reasonably well is something called selective optimization. Okay, sounds like a fancy term. This is what it means. If you have something like a gene that performs a function, so on the left, on the vertical axis here, we have activity, degree of function, and on the x-axis, we have selection round, meaning the stage of selection. Okay, so at the first stage, we take our original gene and we produce many variants of it through mutation. And some of those will have more function, or they could have more function than the original. Typically, they don't, actually, for natural genes. But we'll suppose that in some cases they do. And there will be many different functions if you mutate your original gene. What happens in selective optimization is at each stage you pick the best performer and you carry that one only that one gets carried on to the next stage, where you repeat the process and find variations on that one. And then again you pick the best and you continue until you reach a point where no further improvement is possible. So you eventually reach a point where none of the variants on the current one are better than the current one. And that would be in this graph right here. All of these are worse, so that is your optimized sequence. Okay, so we performed an experiment on this using this beta-lactamase enzyme again. This is the one that enables bacteria to survive in the presence of penicillin. And the green molecule here is penicillin bound in the pocket where this enzyme breaks penicillin and enables bacteria to not succumb to penicillin. What we did is here I'm showing the side chains that enable this thing to fold. What we did is we started with a version of this enzyme that had many many mutations in the side chain, many amino acid substitutions that change these appendages and enable the thing to work, but substantially lower the level at which it works. Okay, so it still is able to inactivate penicillin, but not nearly as well as the natural version of this enzyme. We could show, however, that it is working as an enzyme because, I don't know if you can see it, but there are two red appendages of amino acids in this picture, and I'm going to zoom in by taking out part of the molecule. Here and here, these are critical amino acids for inactivating penicillin, and in this mutant version of the enzyme, we were able to show that these are both essential for its function. So even though the function was very low, less than 1% of natural function, it is an enzyme because it's using these critical amino acids to work. So starting from that low starting point, here's the natural beta-lactamase, full function. Here's our handicapped version that's very low function, 0.3%. We walked it through multiple rounds of random mutation and laboratory selection, and after several rounds, we had recovered more than 100% function. This was measurably more active against penicillin than the starting point. So this is the good example. This is what natural selection can do, and can do quite well. Let's move on to the bad, and then we'll do the ugly. Okay, the bad is described in that same paper. It was Ann Gager and myself doing this work. Again, it uses beta-lactamase, but this time we used a much more radically handicapped version of the beta-lactamase. Here's one of the figures from my book. On the left side, it's showing the normal beta-lactamase with penicillin bound inside the pocket. So up here we have top view, and this is side view. On the left, we have the normal beta-lactamase, and here we have this radical mutant, this badly handicapped version. And you can see in this handicapped version, we've effectively cut off the whole side here. So this is the same view. And we have exposed the pocket where penicillin binds. Normally, it would be tucked in here in order for it to be inactivated, but since we've cleaved off this part, you can see where the penicillin would be. And in fact, we don't think that this version even folds to form this structure. I'm just showing you what structure would be there if it did fold. I don't think it folds at all. But, interestingly, this badly handicapped mutant does confer a very small amount of resistance to penicillin. If you put this protein in cells, they are able to survive a very low amount of penicillin, similar to the one that I just talked about. 0.1% instead of, I think it was 0.3%. This time, however, you walk this through rounds of natural selection and nothing happens. We did several rounds, random mutations to this protein, put it in bacterial cells, test it on penicillin, Petri dishes, and nothing happens at all. What we think the explanation is, as we described in the paper, is that you need to have a fold there, a proper enzyme there, in order for selection to cause these improvements. If you don't have that, even if you happen to have some activity against penicillin, natural selection is not able to improve anything because there's nothing there to improve. So let me read what this says. The lesson is that selective optimization can refine an existing invention, but it cannot invent from scratch. What I think was happening with the with the enzyme that's missing a chunk is that it doesn't fold inside the cells, but it turns out that penicillin, if you just put penicillin in water and let it sit for a couple of days, it degrades on its own. And a little bit of acid, like vinegar or lemon juice, would make it degrade within several hours. It's a fairly fragile antibiotic. And I think this unfolded protein chain just had acid groups that were exposed and slightly increased the natural degradation of penicillin. It wasn't doing anything clever the way the actual enzyme does, holds it and breaks it as an enzyme. Okay, now we're to the ugly one. Here's where natural selection failed where it should have succeeded. Should have succeeded. This is a paper that was written by my colleague Ann Gager, Stephanie Ebnett, Pamela Fahey, and Ralph Silke. It was a collaborative project between Biologic Institute and the University of Wisconsin Superior. Here we have an enzyme called TRPA that is used to make the largest of the 20 amino acids. This amino acid is called tryptophan, and this is essential for cells to make tryptophan. If you look inside, you can see this is where it's working on its molecule to make tryptophan. And if we zoom in, there are two amino acids that are very important for this to work. And one of them, well, my colleagues produced a version of this that has two changes at these locations. And one of these changes was found to completely kill the enzyme. And the other one was found to badly wound the enzyme, but not completely kill it, okay? So what they did is they combined the two mutations, so both of them are present in the gene that makes this protein, and they put this gene in bacterial cells and gave the cells a very small amount of the amino acid tryptophan to grow on, because if they didn't give the cells some tryptophan, then they wouldn't grow at all, okay? So you have a culture of cells growing with a little bit of tryptophan added to their medium. They're able to grow because of the tryptophan that's been given. And what would you expect to happen here if you allow a population of cells to grow this way day after day after day? You would expect, we all expected, I was a part of talking about this project when we were doing it, you would expect that you would get a mutation that would revert the change that kills the enzyme, and then you would have a wounded enzyme, right? You'd expect those cells to grow up and be selected, and then you would revert that mutation and have a fully functional enzyme that makes tryptophan, and the cells would grow like normal. So this is what we expected. You start with this version of the enzyme that has the two harmful changes. One of them totally kills it, and the other one wounds it. You undo, by mutation, by random mutation, you undo the one that kills the enzyme, and then you only have a wounded enzyme that works somewhat, right? So the vertical scale here is fitness. You move up in fitness by undoing the mutation that kills the enzyme, and then you should get the second one reverting, and you have a fully functional enzyme. That's what you would think would happen. 2 steps to very high fitness. That didn't happen in any of the cultures, and this was done in repeated cultures. What happened instead was all of the cultures lost the gene entirely. It's one of the things that Mike B. mentioned. It turned out to be more advantageous, or at least easier, to get rid of this useless gene that wasn't doing anything, and it's costing the cells somewhat to be, making products from this gene that's doing absolutely nothing. All of the cultures just lost the gene. They got large deletions, or they turned off the parts of the gene that enable it to be read. And that was a faster, easier way to save a little bit of energy, and turned out to be that was the path that evolution took, instead of the one that we expected that would have given very high return. We expect something like this because we look at this with intelligence, don't we? We say, here's what you want to do. You want to take this step, and then you want to take that step. That's not how evolution works. It's not looking forward. It is simply doing whatever benefits most immediately. So the lesson from that is, even when a classical Darwinian pathway to high-level function exists, selection doesn't always follow it. Okay. So, despite all the hype surrounding natural selection, we come to this humble conclusion that within limits, selection can refine existing characteristics, but it can't invent, okay? It can take existing structures, whether it's a protein structure or even an organismal structure, and it can do slight modifications of what is already there, but it will never come up with something new altogether. This is very much along the lines of what Mike said. In fact, I have a slide that's similar to one of Mike's. This is actually familiar stuff, that you can get an amazing variety of not just dogs, but lots of different species, including plant species and cabbage and broccoli and things that we eat, corn. But you can only do it within limits. All of these, as different as these dogs are, they're all dogs, right? And they're even very obviously recognizable as dogs. And it's also true that if you took any one of these breeds, like if you took only purebred German Shepherds, you could not reproduce this sort of variation, right? You'd only get German Shepherds, right? If you took any one breed, will breed true, and you will not reproduce this sort of variety. You only get this kind of variety because the wild dog species that humans started to domesticate had a great amount of genetic variety within them, and all that we were doing as we domesticated and as we build these breeds is choosing out aspects that we want in a breed, right? And some of these breeds, by the way, would not do very well. That guy would not do well against wolves, would he? So you wouldn't have found that in the wild, but you have the potential for making Chihuahuas and small dogs and all these things in the natural wild dog populations. But once you've purified out one version, you've lost that variation and there's no way to get back that variation, okay? Again, you're losing things, which is what Mike was talking about, not gaining things. This is actually not new. The idea that natural selection does not explain invention has been around for a long time. People have been saying it ever since Darwin's day, and yet it keeps being ignored, so people have to re-say it over and over and over again. In my book, I quote Hugo de Vries, who wrote a book in 1904 where he was quoting a friend as saying, natural selection may explain the survival of the fittest, but it cannot explain the arrival of the fittest. That has kind of a nice sound in English. I'm not sure if it makes it into Portuguese, but it rhymes in English. It probably doesn't in Portuguese. But that became a phrase that has been repeated many times. Natural selection explains survival of the fittest. It does not explain arrival of the fittest. Even as recently as 2014, a Swiss biologist named Andreas Wagner wrote a book that was titled Arrival of the Fittest, that was addressing this problem that has never been solved. And he says in that book, natural selection can preserve innovations, but it cannot create them, which is exactly what we're saying here. So, I think the title of my talk was How We Know That Proteins Were Designed. And you might say, well, Doug, you've only shown us that they didn't evolve. You haven't shown us that they were designed. But I go back to something that I said in yesterday evening's lecture, if you were there. Really, when you eliminate, there's a logic here that allows us to eliminate not just Darwin's explanation for enzymes, but all accidental explanations of enzymes. And it works like this. In yesterday evening's lecture, I had a picture of a bird here, of a crane, but let's put an enzyme here instead because it's the same thing. When we look at something like this and we realize that someone had to know how you arrange the amino acids in order to get this to work, then we attribute it naturally to genius. Somebody knows how to do this. I don't know how to do this. And in fact, after decades and decades of very smart scientists studying all kinds of proteins, we still cannot author amino acid sequences that fold into functional proteins. We still don't know how to solve this problem. It's called the protein folding problem. It remains unsolved. So somebody brilliant knows how to do this. When we look at things like this, we naturally intuit that genius is behind this. So anyone who wants to claim otherwise is claiming that accidental causes just happen to do the work of genius. And because those two causes are so very different, polar opposites, that could only be true by a remarkable coincidence, a fantastic coincidence, even an implausible coincidence. Probability is the math of coincidence, and when you do the math on this, it turns out that that's just not possible. The only way to avoid this problem of coincidence is to reject accidental causes and to affirm that these things look like they were designed because they were designed, okay? I will finish with that. I will also show you, I had someone asking about the book, just to see what the cover of the book looks like. Came out last year. It's called Undeniable: How Biology Confirms Our Intuition That Life is Designed. Thank you.
Nós vamos passar agora para a sessão de perguntas e respostas. Eu espero que vocês todos tenham as suas perguntas prontas aí. Vamos convidar os três palestrantes para estarem aqui na mesa. Mike, Brian, Douglas, please have a seat on the table. And we have a gente vai ter a tradução instantânea. Vocês veem que a moça é bem rápida, né? Ela traduz quase que imediatamente. Então, a gente está chamando de instantânea a tradução. E você pode fazer a pergunta. Have a seat, please. Yes. We all sit on the table. A gente vai fazer você pode fazer em português ou em inglês, porque a gente tem a tradução aqui funcionando. E vamos lá, gente. Olha, quem gostaria de fazer a primeira pergunta? Bruna, né, Bruna? A Bruna está pronta ali? Olha, a primeira pergunta. Nós vamos fazer assim uma regra com as perguntas. Você tem que fazer a sua pergunta em 1 minuto. Tá bom? E os palestrantes vão responder. You have up to 2 or 3 minutes to answer. Don't take too much time to answer the questions, so we can have as many questions as possible. Tá bom? Olha, tenta perguntar em 1 minuto e eles vão tentar responder em 2 ou 3 minutos cada uma das perguntas, tá bom? Seja bem sucinto na sua pergunta.
Meu nome é João Marcos, eu sou médico. Eu quero fazer uma pergunta sobre a opinião de vocês sobre o atavismo, erevismo. Assim, a gente observa alguns fenômenos na natureza, como lista de zebra em cavalo. A gente observa alguns bebês que nascem com rabo, com tail. Então, assim, qual a opinião de vocês dentro da escola dessa escola nova, né? Que para mim eu sou novato, estou tendo conhecimento agora. Qual seria a explicação para isso, para o fenômeno chamado atavismo?
Bihi, I guess he's willing to take of this atavism.
As far as humans with tails, I think that is very controversial, that some of the examples that have been shown have been determined to be staged, faked. Perhaps some infants are born with a fatty deposit around the end of their back, but it's not a true tail. So that well-known atavism is pretty shaky. As for other ones, the closer one looks, the more the atavism looks kind of doubtful. There was a paper a year or 2 ago that published an assertion that the cells from chickens could develop or could code for teeth, or that a chick embryo, I've forgotten the details, could develop teeth. But when you looked at the details of the paper, which I forget, it actually did not support the press reports that most people read. As far as stripes in zebras and horses, that's an interesting observation, but one can imagine that is a fairly minor change. It's just a different color pattern. It's nothing really new structure, new function. So I think the atavisms are oftentimes exaggerated, and they make for interesting reading when you're at the grocery store and taking a newspaper, but I don't think they have very much evidence behind them.
What you see is a very clear pattern that when people don't understand what something does, they say it's poor design, or they use vestigial structures. But what you see as science advances, consistently what they used to think was poor design, they realize is good design. So in the 1800s, people identified over 100 features of the human body that they thought were useless remnants of the past, things like the gallbladder, the pancreas. Obviously, today, people realize those have real functions. More recently, people thought the appendix was useless, but now they realize it plays a role in the immune system. People used to think that the backwards wiring of the eye was a poor design. They now know it's essential to give the photoreceptors the nutrients they need. I call it the Darwin of the gaps argument. What people don't understand, they might say is poor design, but consistently, as science advances, they see it's very good design. Junk DNA is a classic example.
Ok. A primeira pergunta já foi? O segundo? Ali. Muito bem. Seja bem sucinto, tá bom? Bem claro também na pergunta, tente. Porque vai ser traduzida. Não pergunte muito rápido também, por causa da tradução, tá bom?
Vou tentar. Isso. Bom dia, meu nome é Douglas. Eu gostaria de perguntar para os senhores o que falta para a teoria do design inteligente ter o mesmo tipo de aceitação na academia, por exemplo, como a questão da filosofia, que da década de 50 para cá houve uma revolução, Plantinga, Swinburne e outros, eles conseguiram fazer essa quebra de paradigma e hoje a filosofia ela é aceita na academia como a filosofia, no caso o teísmo cristão é aceito como uma proposta acadêmica. E o que falta no design inteligente para que ele seja também considerado na academia como uma proposta científica razoável.
Was that to me? Yeah. Does this work?
Yeah, it's
Hello? Yeah. That's a very good question. I don't know the answer, but I don't think what will happen is, I don't believe that our work is ever going to cause Richard Dawkins and people like him to give up what they're saying and to accept intelligent design. What I'm very hopeful of is that our work will be increasingly followed by young people who are the next generation of scientists, and increasingly the young generation will be disenchanted with the Darwinian model of origins, and what will happen is the people with the old ideas will retire out of the academy and they'll be replaced by people who have new ideas. That's what I think is going to happen.
Exatamente. Mais alguém? Deixa eu estou me aguentando aqui, mas é exatamente isso que a gente precisa fazer, viu? A gente precisa esperar, é o tempo que vai mudar, porque o pessoal que está aí não vai mudar, e a gente tem que divulgar o design inteligente o máximo possível para a nova geração. É essa a resposta perfeita. Mas you want to comment on that, also? Bihi, Brian? No? Okay. Next question.
Eu não sou cientista, mas um físico nuclear, me fez uma pergunta. Primeiro, ele fez uma afirmação de que a mecânica quântica não combina com o design inteligente. E porque a mecânica quântica é muito aleatória, é totalmente aleatória. E isso, na ideia dele, confirma a aleatoriedade da evolução, né? Então, a minha pergunta é, como que o design inteligente enxerga a mecânica quântica? Como que eu posso responder a ele essa pergunta?
Well, quantum mechanics talks about the very small structures in the universe, like an electron going around like an electron going around a nucleus. And it's not random, it's defined by very specific equations, Schrödinger's equations. So it describes the probability distribution in a very specific way. And as it turns out, the equation that defines quantum mechanics has to be very precise to create atoms, hydrogen, helium, the whole periodic table. If that equation were even slightly different, there wouldn't be chemistry and there wouldn't be life. So quantum mechanics points very clearly to design. Now, what it does tell you is that there is probability built into the structure of our universe. But the way it's built in is in such a way that allows for life and points to the design of science.
Perfeito. A mecânica quântica aponta para o designer, não é? Ou seja, as equações da mecânica quântica são... Já viu a equação de Schrödinger? O cara é exibido e exagerado, não é? Muito bem. A próxima, quem gostaria de perguntar? Com quem está? Ah, sim.
Meu nome é Deise, eu sou de Maceió, sou bióloga. Mas eu gostaria de entender essa relação entre o design inteligente e a economia. Porque o DI, por exemplo, lá nos Estados Unidos, existem pesquisas sobre liberdade econômica e eu queria entender essa relação.
I think Steven could, yeah.
Is this on?
Yeah.
So it's an interesting question. I think one of the things that define. Can you hear me?
Yeah.
One of the things that is common in Discovery's program is information, which you've heard about from our scientists here. We have a new approach to economics that talks about the economy as an information theory, meaning that what drives an economy is not carrots and sticks, it's information. And I'll try and explain it very briefly. In an economy, information is something that is new. New things that are brought into the economy are entrepreneurial pursuits and tests in the economy. So you start a business or you have a new idea. It has to be tested in the economy. You're injecting new information and it has to be allowed to succeed or fail. That information is driven by an entrepreneur. And what this really does, I think at its core, is challenge the idea that free enterprise economics, capitalism is driven by greed. Because we know, most of us would agree, greed is not good. So information theory says the economy is not driven by greed or self-interest, it's driven by the altruism of and the good nature of the entrepreneur who tries something to build a business and has to think of the customer before he thinks of himself. And that new entrepreneurial pursuit is information that's new, that's not predictable, and that can't be assured of success. Because if it could, socialism would work, and we could plan an economy. But the reality is, in economics, information theory plays a role in determining what works and what doesn't, and you have to have a platform in economics where those experiments can be undertaken, and that's the free market system.
Perfeito. Próxima, quem gostaria? Davi? O microfone. Não, Davi, você tem uma antes, pois não? Se puder falar seu nome e perguntar rapidinho, em 1 minuto, e lento, não muito rápido, tá bom?
Meu nome é Vitor, eu queria fazer 3 perguntas, se for possível.
Uma, Vitor. Uma só.
Tá, a respeito
Escolhe uma, isso.
A respeito do que os darwinistas eles combatem o design inteligente. E um dos combates deles é com relação à falácia de Hoyle. Eu acho que vocês já devem ter ouvido falar. Eu queria... que tem a ver com esse processo que, na prática, se eu for fazer a sopinha de letra, não necessariamente ela tem a mesma chance de eu formar cada letrinha. Então, dizendo os darwinistas, tem alguns processos naturais que apontam em alguma direção, como superfícies equipotenciais que têm um mínimo, como gradientes de pH. Então, eu queria ouvir, né, sobre vocês, qual que é a opinião do design inteligência contra esses argumentos.
I might need to clarify the question. Are you asking, Darwinists will say that evolution doesn't have any predefined endpoint. It can go wherever it needs to go. And so some of them will think that we are cheating when we ask whether it's possible to make a particular thing, because evolution could go anywhere. Is that your, have I understood the question correctly?
Na minha pergunta é no sentido de, por exemplo, vamos supor que eu tenho vários aminoácidos e eles vão formar uma proteína. A pergunta é qual que é a probabilidade daqueles aminoácidos se juntarem para formar aquela proteína específica. A falácia de Hoyle que eles utilizam, eles falam que a ACTAG, eles podem se organizar de acordo com processos naturais, como gradiente de pH, como superfícies mínimas de potencial. Então, falar que a CTAG eles vão se organizar com a mesma probabilidade, no argumento deles é uma falácia. Então, essa é a minha pergunta.
Okay, there's parts of it that probably got lost in the translation, but it is not the case that ordinary physical processes will self-organize amino acids to form functional proteins. What we were testing in the lab was how rare are the combinations that are needed in order to fold into a functional form, and we find that they're extremely rare. And if you do random mutagenesis in the lab, or if you let populations randomly evolve, they don't find these targets because they're just too rare to be found. So there are a number of, you have to understand that Darwinists want to refute intelligent design arguments, and some of them are quite desperate to refute them. But if you examine carefully what they're saying, it really does not make sense.
Muito bem, a próxima, Bruna. É o Davi, né, Davi? Você. Quem quer fazer pergunta, levanta bem alto a mão para a Bruna poder ver. Aí a gente marca mais ou menos uma sequência. Davi?
Meu nome é Davi Oliveira e eu gostaria de fazer uma consideração e queria que o Dr. Mike Beer fizesse a contrapartida. Me intriga uma coisa em relação à questão da malária, é que você tem um gene sendo quebrado, e eu entendo, e até uma provocação, uma suposição, que poderia ser um gene inativado, que tinha uma inteligência, e que, quando foi provocado, deu informação para fazer aquela quebra, e essa provocação veio por um efeito externo. E aí, essa primeira população sofreu, mas teve condições de passar para outra população adiante essa informação que estava adormecida lá, que já fazia parte da inteligência do parasita e que foi ativada. Eu gostaria que o doutor fizesse consideração sobre essa minha suposição e até uma provocação. Obrigado.
Well, that is an excellent question, and there are some scientists I know who are sympathetic to intelligent design who do think that organisms are built to adapt to their environments. But in the cases that I presented during my talk, I don't think it's necessary to suppose that that is the case, that a designer built them so that they would have the ability to break in the presence of modern-day antibiotics, for example. In the case of, say, the malarial parasite, it has a molecular machine which can get rid of the waste from eating hemoglobin. It can't eat all of the hemoglobin. There's a part called the heme, which it can't eat, and it has to get rid of that. And chloroquine, it turns out, but can bind to that machine and stop it from working, like throwing a wrench into a a motor or machine. It stops it. And the changes in the protein or the molecular machine which allow it to be resistant to chloroquine are changes which prevent the chloroquine from binding to it. But it also kind of messes up the ability to get rid of the waste, but it allows it to proceed just enough so that it survives. And if you look at the probability of that happening, the probability of malaria developing those changes is pretty much what you would expect just from random changes happening to amino acids at the rate that we know they usually happen. And so there's really no need, I think, to postulate that that feature was designed. It's in any complex machine, any complex system, you have the possibility of changing something or getting rid of something so that it can work better in a specific circumstance. Let me give you an example from our everyday world just to try to make that clear. Suppose that your life depended on your car getting better mileage, gasoline mileage. You could go further on a liter of gasoline. How could you quickly change your car so that your car could get better gas mileage? Well, one way you could do it is you could snap off the side view mirrors, and that would reduce the drag from the air resistance as you went forward. Of course, side view mirrors are useful, but if your life depended on it, well, maybe that would be the best thing to do. Another thing you could do is, say, take the hood of the car and throw it away, and that would lighten the car. Of course, now rain would get in your engine and stuff like that, but your life depends on it. That's the first thing you have to do. And nonetheless, cars were not built to get better gas mileage by breaking those things off. That's just kind of a side effect. It's just a coincidence. So I don't think we have to say that organisms were built to do exactly that. Maybe in the case of polar bears and so on, but not antibiotic resistance.
Ok, Bruna, próximo, sim.
Hello, thank you so much for your lecture. So my question is for Dr. Brian Miller. Using the same slide you used in your beautiful presentation, Dr. Gerald Schroeder from MIT as well, he said that he provoked a good argument, and I just would like to check with you what you think about. He says that there are 4 things in the set of forces involved in the expansion of the universe. So the first one is the set of forces not physical, acts on the physical, created the physical from nothing, and predates the universe. And he concludes, this is the definition of the biblical God. Not physical, acts on the physical, created the physical from nothing, and predates the universe. Do you agree with this Jewish Orthodox scientist's view? Thank you so much.
That's an easy one. Yes, I agree. But I think there's a very important point to make. One is all those arguments point to a God who created our universe. That's important, a God who's transcendent, non-material, eternal, infinitely powerful. But when you look at the evidence for the perfection of design of our planet, our sun, our moon, that shows that the God is not distant and outside of our universe and is not a deistic God, but was involved in shaping the way our universe developed. And when you look at the origin of life, you see that God created life at the level of DNA. It's kind of like when Jesus talked about how a sparrow does not fall outside of his will. So it points to a God that's not just transcendent, but immanent and intimately involved with our lives. So all that together points very clearly to the biblical God.
Could I just add
Yes,
something?
sure.
Yeah, and that was the point that I was trying to make also in my talk when I had the slide trying to show where the edge of evolution was. And the top was the laws of nature, and then constants, and then the strength of interactions, and formation of galaxies, and then origin of life. Design is not just at the laws of nature. It descends way down, and I think it's to the level of families. All of that is of a piece. All of that is needed for design at a very, low level of creatures. So yes, it's in the grand laws of nature, but it all descends very far.
Ok, a próxima pergunta, Bruna, cadê você? Tem um ali, depois você, tá bom? A gente tem ainda alguns minutos.
Eu sou Valdo Pereira, meu nome. Eu sou engenheiro florestal. Tomando esse gancho, né, que nós entramos nessas questões de ordem teológica, quando o Dr. Michael Behe, pela explanação dele, deu a entender que ele acredita na ancestralidade comum e que o darwinismo não tem esse poder todo de fazer com que de uma única célula nós venhamos a acontecer essa evolução a nível de chegar no homem. Então, nesse meio tempo da ancestralidade comum, de uma simples célula, até chegar a um homem, nesse período, você acredita que houve intervenção divina para que isso pudesse chegar naquilo que nós podemos chamar de princípio antrópico?
That's an excellent question. And I will speak as just a biochemist, not as a Christian, because there's many better Christians around here and many better trained in theology than myself. As a biochemist or as a scientist, you can determine that something was designed, but determining how it was designed is a much more difficult problem. As an example, there are arrangements of rocks in Stonehenge in Ireland, is it? I'm thinking Ireland. Or England, I'm sorry. In England, that people knew were designed but didn't know who built it or how it was arranged for a long time. Some pyramids and so on, people know immediately they're designed, but didn't know exactly how it was done. There is perhaps you've heard of it in the United States, there's a monument called Mount Rushmore, where the images of the faces of 4 presidents of the United States are carved into the rock. And if somebody who hadn't heard of it before drove by and looked up and saw those faces, they would immediately know that it was designed, but they wouldn't know how. It could have been blasted in by a laser beam from space aliens, or it could have been, something else. It might have been carved 1,000 years ago, as far as the person just seeing it knew. So the point is that it's very hard to tell how something was designed, but it's simple. You immediately perceive design in the purposeful arrangement of parts. So the question is, would God have to infuse information at different points along the way to guide things in the right direction? Maybe. That's, as far as I know, that's possible. I would say we don't have scientific information to say that had to be the way it occurred. It could have been programmed somehow into nature from the beginning and unfolded without what we call intervention, which is a bad word, without further action by God. There are many possibilities. And so in my books, I have written that we can easily tell that something was designed, but the question of how that was done and many other interesting questions are still open.
Can I add a little bit on that? Let me also say, I know Mike said yesterday evening, I think, that he, for reasons of prudence, has not challenged Darwin's tree, right? Because he's already challenging something else, and he wants to limit the battles, okay? But I think people should know that advocates of intelligent design do not all support Darwin's tree, and I think Mike is willing to be skeptical of that as well. I'm very openly skeptical of a universal tree of life. I think it's a construct that is so attached to Darwin's theory that people desperately want it to be true. Evolutionists desperately want it to be true, and whenever scientists are in a position of wanting something to be true, there's a tendency to see, to always interpret the facts as confirming what you want to be true. So I am a design advocate who's very skeptical of the tree of life, and I openly admit that.
Perfeito. Olha, nós temos a última pergunta ali, Bruna. Última, viu, gente? Desculpa, mas a gente vai ter mais uma rodada no final da tarde com todos aqui, tá bom? Brasileiros e americanos. Sim, seu nome e a pergunta, bem rápido.
Hipólito, da Sociedade Criacionista. Sociedade Criacionista Brasileira de Brasília. Minha pergunta é a seguinte, eu já fui um ateu, já fui um evolucionista, e não precisou muito para mim, ao começar a enfrentar, ter coragem de estudar o assunto da ciência sobre a criação, sobre a evolução, não demorou muito para que eu pudesse entender que o evolucionismo era uma fraude. Isso não foi difícil para mim. Argumentos como a falta, no registro fóssil, a falta de espécies de transição, ou dentro da física, a segunda lei da termodinâmica, ou dentro da biologia, o livro do professor Michael Behe, quando fala da complexidade irredutível, são argumentos, ou mesmo na química, a energia livre de Gibbs, que impediria a existência da formação inicial de RNAs que pudesse desenvolver a vida e tal. Cada um desses argumentos sozinho, por si só, já convenceria uma pessoa honesta da impossibilidade da existência da vida que não fosse por meio de um design inteligente. Então, eu pergunto, o que leva uma pessoa, dentro do ambiente científico, a não acreditar no design inteligente?
Maybe I'll start on that one. Yeah. That's a very good question. In my book, I actually spend several chapters talking not about science itself, but about the culture within which science occurs. And I tell the story of how I was removed from my position in one of the top laboratories in Cambridge. And my removal had nothing to do with me misbehaving or doing bad science. It had everything to do with the political tension around the challenge to Darwinism. So actually, I start my book talking about an interesting thing that is recorded in the various editions of Darwin's book. By the 6th edition, which was the final edition, which came out in 1873, I believe, or 1872, there was a paragraph or two coming after an original paragraph that said, Darwin said from 1859, virtually, he said, none of my peers agree with this theory. Why is that the case? And he said, it can only be that they're stuck on their old ideas, and so I look forward to the young generation, the up-and-coming generation, to view this with an open mind. That's what he wrote in 1859. By 1873, he kept that paragraph, but followed it with a paragraph where he said, now the situation has totally changed. All the naturalists admit to this evolutionary phenomenon that I'm describing. And what I say in my book is what happened in 10 years to change everyone from being opposed to Darwin's theory to accepting it. It was not a matter of science. There was no data that changed their minds. It's a culture shift. Scientists are humans, and if nobody wants to be excluded from your own professional culture, and peer pressure is very much at play in the sciences. So I think more than the question of what is convincing in evidence, peer pressure plays a strong role in what scientists believe. And the history of science bears this out, because everyone tends to fall in line with the orthodox position of the day, regardless of whether that position is true or false.